history, kind of this science. And I think I've told you, the older I get, the more I kind of appreciate history. Oh, I found out this right here, maybe some of you heard me asking it. No, where to go? Come back. Not that one, this one. This guy, okay, it wasn't the Aztecs, it was the Incas. Oh my gosh, and thank you, Mr. Evans, he is so great. He said it was the Incas, and there's this awesome, crazy story about, well, it's not so awesome, about the Spaniards and conquering and taking their king, and he tells such great stories, they're true. So anyway, the point here was there are cultures like the Incas that would study the movement of the sun across the sky and kind of know that the sun gets lower and then highest in the summertime for us, even at noon. And the whole moon thing, I mean, that's just awesome. So other cultures would respect the cycles, and so they would build accordingly. So this actually, with regard to history, there are some people out there that think that our Earth is flat, and I'm not here to give them a hard time. But one thing, you might think it's flat because you just look out and you don't see it curving, right? Well, this was an experiment done in the year 240 BC, a little experiment. Can you imagine this? And so I don't know how they coordinated this. This is amazing. But they had a person with the sun overhead, okay, would go ahead, and then there was a person that was a certain distance away from them, and they looked at how the sun, the sun, instead of being overhead, it was at an angle of 7 degrees. And the reason it wasn't overhead is because it wasn't flat between these two people. If it was flat between those two people, the sun would be straight up for both of them. But here, the sun was at an angle of 7 degrees. And that bend in the earth actually that 7 degrees represented 7 degrees out of 360 degrees that our earth is shaped like a circle. So basically, if you take the ratio of, they can come up with the distance here. Is that right? Yeah. 7 360ths of the Earth's circumference was represented by this. Okay, so they could come up with that distance and then multiply it by 360 over 7 and get the Earth's circumference, the circle of the Earth. Isn't that cool? I know. So anyway, that's neat. Oops, that isn't what I wanted to do. Come back here. Oh my goodness. I'm glad it's Friday. How about y'all? And I hope everybody's going to go out to the picnic in a little bit. Okay, that's what I wanted. Hopefully, I've been kind of kidding around about, what's this?
Chair.
It's the sun. It's a chair. It's a stool. It's the sun right now. Yep. Okay. And we kind of take for granted that we all know that the planets orbit the sun, right? But that wasn't always the case. And I'm going to kind of talk a little bit about the history. The last person, well, actually, before this is called a sun-centered model. Does that make sense? Sun-centered model. Before there was that, there was the geocentric model. This guy right here. Geo meaning Earth. So instead of this, it kind of makes sense. I can see why people would think that. Instead of that, they thought that the sun orbited the Earth, geocentric. The geo meaning Earth. The Earth is in the center. So the sun orbited the Earth, the stars orbited the Earth, the planets orbited the Earth. Okay, they thought that. And so it looks kind of like this, where there's the Earth, there's our little blue ball, and then these are kind of the things that orbit the Earth. Well, honestly, I don't, can't fault anybody for that, because that's kind of what it looks like a little bit. In fact, we even come up with a scientific model called the celestial sphere that has the Earth in the center. But that's not the way it works. Okay? So geocentric means the Earth in the center. Heliocentric means what in the center? The sun, yeah. Helio. Okay, that means this model. So back in 260 BC, clear back that far, who was it? Aristarchus actually said, this is the way our, at the time you probably called it the universe, this is the way our universe works, that the planets actually go around, or Earth anyway, probably didn't know much about other planets, but that the Earth orbits the sun. Well, there was a fair bit of, that didn't take, let's just put it that way. This idea of having, and I kind of moved this slide, so if you print out my slides, they're out of order. But this is that geocentric model. It has the Earth in the center and it has the sun orbiting the Earth. Actually, Ptolemy, back way after, well, after Aristarchus by what, 400 years or so? Ptolemy in 100, 170 AD, he was kind of the last big guy who was like, no, it's geocentric model. The sun orbits the Earth, okay? In fact, though, we're going to kind of, well, I guess I wouldn't necessarily revisit this, but do you remember the keep it simple, stupid? Yeah, that's actually in science, we try to keep things simple. And what Ptolemy did was he actually came up with a way to go ahead and make a geocentric model, so the sun orbits the Earth and the stars orbit the Earth. But he had to kind of throw in some twists, and his twists were these epicycles. Specifically, the epicycles that Ptolemy came up with was to talk about why the planets, when we look at the planets in the nighttime sky, why the planets do what they do. And I'll try to describe what they do and what these epicycles try to describe. Okay, so Ptolemy, geocentric model, and he got things pretty complicated by introducing these epicycles. Before I show you what the planets do in our nighttime sky, picture that little yellow orb there as a planet. That little orb there, that planet is going to actually orbit the Earth. I know it's pretty weird. You're like, really? This is what really happens. But in order to explain the motion of that planet, it had to, every once in a while, go in these cute little epicycles. So let's see if I can do this. The planet would go kind of, the way I think of it is the planet would go like this and then would go on an epicycle. And then would go like this and would go on an epicycle. Go like this and go on an epicycle. Okay? That's what the planet did. Now, what he was explaining was this is what we call direct motion. Okay, this is direct motion. He had to describe what we call retrograde motion. And if you're into astrology, okay, I'm kind of showing you direct motion, retrograde motion. Astrology kind of talks about this big hairy deal. The planet is looking like it's going backwards in the sky right now. Okay, and it really does. But I'm going to show you why that phenomenon happens, not with the geocentric model, but with the heliocentric model. Okay, so Ptolemy, kind of the last of the geocentric model people. So the word planet actually in Latin means wanderer. Let's see. I was going to try to show you. Let me see if I can. I want to try to bring up that. Anybody else use the stellarium yet in here? Stellarium? Remember, it's free. It's the one that I kind of refer to. I want to show you kind of a wandering planet. And I tried to do this before class. Let's see if it works for us. Now, for those of you who were out on the hill the other day, what planets, 2 planets did you see? Saturn and Jupiter, exactly. So let's kind of take a look at those. In order to see them, we're going to have to make it darker. Let's go, oops, let's not do that. Let's go, instead of 10 a.m., that's 8 p.m. Let's go 9 p.m. No, let's go 8 p.m. Okay, and let's focus on Saturn. Saturn, I'm going to go ahead and add some constellations here. Okay, let me go ahead and add some names. Oh, isn't that cool? So right now, Saturn is in Ophiuchus. Okay. Now I'm going to go down here and I'm going to fast forward. I'm going to fast forward from today to tomorrow. And it might be kind of subtle. Let's see if we can see Saturn move against the background stars. It's very subtle, isn't it? That's day by day. I'm going to go a month. Okay, so right now it's kind of in kind of the leg of Ophiuchus. I'm going to go a month from now. Okay, it's still in the leg of Ophiuchus. I'm going to go a month from now. And I got to find Saturn. Oops, I wonder if that's going to work. Oh, well, it's kind of at dusk. But finally, did you see Saturn move? I don't know if you saw it move. Okay, it's moving this way. It's moving westward. It's a wanderer. It doesn't stay with the constellations. Now, I had to go a whole month to kind of show it move. It doesn't move over the course of a night, but it does over the course of day after day after day. Okay? And the reason for that is, I'm going to go back to the heliocentric model. Let's see, I need extra things. So is Saturn inside our orbit or outside our orbit? It's outside our orbit, yes. So Saturn's over there. So here's the deal, but Saturn's relatively close compared to Ophiuchus stars. Oh my gosh, Ophiuchus stars are way out there. So as I move on the Earth, this is Saturn, as I move, Saturn does appear to change its position against the background stars. That's why Saturn moves. Okay. Is Saturn orbiting the sun? Yeah. But Saturn actually is moving more slowly in its orbit around the sun than the Earth is. So that's why we see it move. Let's see. And then to get out of here, you have to, well, there's a few ways. You can shrink it down like this. We'll let it run in the background. So back to the whole historic sort of thing. Oop. So the word planet means wanderer. So I just think it would be neat to be back in old-timey where you saw them wander against the background stars. But you also recognized that there were patterns. So the planets have what we call direct motion against the background stars, and they have retrograde motion. The direct motion is this, is kind of similar to the way the sun moves against the background stars. Okay. Direct motion can be explained, check this out, direct motion can be explained if the sun, planets, and stars orbit with the Earth in the center. Isn't that weird? Okay, so direct motion is like the planets on direct motion. But sometimes they appear to reverse themselves. They go westward, and we call that apparent retrograde. A lot of times I won't say apparent, I'll just call it retrograde motion. It's the backward motion. And this is showing you, this little dot here is Mars, not Saturn, but it's Mars, also an outer planet. And it's how Mars would look against the background stars. Let's kind of find our bearings. It looks like it goes June, July 30th, September 30th, okay? So did you catch that loop-de-loop? It starts here against the background stars, moves over here. That's all direct motion. This right here is retrograde, and then this right here is direct again. Okay, so this is backward motion. And I'm going to show you why that happens. You're like, oh my gosh, this is another hard thing in this class. But you can prove this to yourself if you pull up Stellarium and kind of inch it through month by month and kind of see it against the background stars. This, I have 2 slides to try to show you why retrograde motion occurs. This is one of 2 slides. Of course, the kind of colorful outline means it came from OpenStax. So the way this works is this guy right here, the Earth is the A, B, C, and D. That's the Earth orbiting the sun. Mars then is this, A, B, C, D, E. You see, what, 5 locations? You see 5 locations for the Earth and 5 locations for Mars. Does it look like Mars is taking a little bit longer in its orbit? Okay. So, here we go. At location A from the Earth, notice A from Mars looks like it's A here against this background stars. The Earth is moving more quickly. Here's B for the Earth. Here's B for Mars. And notice now it looks like Mars has relocated. This is going to be our direct motion. From A to B is direct motion. It's gone that way against the background stars. Just because Mars is relatively close, and it's a parallax thing, actually. Okay, it's not part of the constellation of stars. It's relatively close, so we see it move. Have you ever, have you ever kind of got a dizzying feeling if you're driving down the road, someone's coming up, you're in the right lane, somebody's in the left lane, they're moving faster than you, and if you're kind of looking out against the kind of the background, when they come up on you, it almost feels like you get the sensation like they're moving backwards, and then they pass you, and then you're both going in the same direction. You're like, I have no idea what you're talking about, but if you know what I'm talking about, then you felt it. What's happening is as that truck or whatever who's like going so fast down the road, they shouldn't be driving so fast, as they catch up with you, this phenomenon happens. It kind of looks like they're going backwards, but then they catch up. So let's see what that looks like. So A and B is direct motion. Now C, if you look where the Earth is and you look where Mars is, it looks like Mars has gone backwards at that point. That's kind of like the vehicle catching up with you, the vehicle's going to pass you, but that's kind of a backward motion against the background. That's what it is. Okay? So what happens then as the Earth goes ahead and surpasses, it's the fast lane, it goes ahead and it passes Mars up. Now we see D. D looks like it's still going backwards, I think, between C and D. But between D and E, notice then that it looks like it's going forwards again. It's kind of a meeting of the planets in their orbits. And the fact that they go different speeds. Always the outer planet will go more slowly. You might say, well, Mrs. Snipes, what kind of question would you ask on a test about all this? Well, I wouldn't ask you to explain it because it's kind of hard. But I might ask you something about why we have this phenomenon of retrograde motion. And I hope you would say something like, it's because the inner planets move faster than the outer planets. Okay, that's kind of what I'm after. Okay.
Can you use like parallax to help explain that?
Yeah, I think parallax because we see them move against the background stars because of parallax. Yeah, I think so too. Yep. And this is from a different textbook, and it's kind of showing you how this person on the blue circle is the Earth, this person on the red circle would be another planet moving more slowly. And you can kind of see a similar phenomenon against the background, and this is back to the planets. So, yeah. It's cool. So it starts with the letter P, but pronounced with T. Who did I say was kind of the last lone holdout for the geocentric model? Ptolemy. Very good. Isn't that weird? It starts with P, but it sounds like a T. Ptolemy, yeah. So then here we have kind of re-enlightenment, or scientists do this all the time when they're wrestling with things. This guy brought up Aristarchus' idea of let's go ahead and make it a heliocentric model of our universe. It's funny to think of how our universe is expanded since our knowledge is expanded. Our universe at the time, let's go ahead and put the Earth going around the sun. So this is Copernicus, and he kind of brought it up again, basically, okay? Now, as Copernicus goes ahead and begins the whole heliocentric revolution, the whole sun at the center and the planets over the sun, you're going to kind of see this trauma unfold between science, quite frankly, and religion. There's a little bit of a tension there. And in this case, it was because if you go ahead and you take not the Earth at the center of the universe, but instead you put the sun at the center of our universe, you have demoted the Earth in a sense. So there was a little bit of pushback here. You're going to see that with Galileo. So here, Sol, what's that stand for? Sun, dun, dun, dun. Yep, so there's the sun. We got Mercury, Venus, Terra, Earth, Mars, Jupiter, Saturn. I don't think that's, I think that was the last planet I knew of, I'm guessing. So this is Copernicus. Yay, Copernicus. So we have a few more names after Copernicus, okay? So the next name after Copernicus would be Brahe, Tycho Brahe. And is this the dude? I'm pretty sure. I bet Mr. Evans knows. I think this is the guy who lost his nose in a duel, I think, because sometimes you see pictures when he's got like a fake nose, Tycho Brahe. When I think of Tycho Brahe, I think of like nobility and a kid with lots of money. And so with lots of his money, what he did was build awesome toys, okay? So he didn't have the telescope necessarily. Well, the telescope was there, but it was Galileo that used the telescope to, we're going to see here in a minute, that used the telescope to look at the objects in the sky. But what he did do was to do really precise measurements of things, including those wanderers. He made precise measurements of like stars that stayed in constellation patterns. And then he saw these wanderers, these planets. That's Tycho Brahe. After Tycho Brahe, we had Kepler. And sometimes I get I think we're okay. So he was still alive, 1601. And I'm pretty sure Kepler was a student or somebody that Brahe brought in to kind of mull things over. Because Brahe was looking at these wanderers, and one thing scientists like to do is once you see this wandering planet, you're like, can I predict where that wandering planet is going to be at a certain time? And Brahe couldn't. So he's like, okay, Kepler, look at my data, see what you think. So Kepler comes in, and he takes a look, and what we're going to see is that actually Kepler, this says his discovery of the basic laws that describe planetary motion. Kepler came up with, I'm going to talk about 3 laws of what the planets do, because it was these wanderers that really got Brahe, everybody in the tizzy. Remember, it was these wanderers that made Ptolemy come up with these epicycles, okay? This is a picture, we're going to be talking more about this. Some of you guys love this idea of stars blowing up. Stars blowing up. This is what we call the event when a star blows up is a supernova. There's 2 types of supernova. This, and then what they leave behind is called a supernova remnant. So this is a supernova remnant. I think this is M41. So back in 1957, Tycho Brahe actually looked at the sky one day, and it was normal, and they looked at the same sky the other day, and he saw this brightness that was from a star that blew up. Okay, so that's significant. He also found comets. Okay. All right. So yeah, this says that Tycho Brahe, the dude that wasn't spoiled, I don't know, he had a cool way of looking at the sky and writing down lots of data, but he needed the mathematician part that Kepler brought. Okay, so Kepler's breakthrough. Kepler's big breakthrough then, the biggest, well, there are several of them. But one of Kepler's breakthrough had to do with his first law. That's the sun, and this is the Earth and all the planets, and what's the sheet paper called? Where they all orbit the sun in, what we call the ecliptic. The ecliptic, or the plane of the ecliptic, perfect. So this kind of goes a little bit back to the religious aspect. So it was hard to go ahead and break from this idea of the Earth being the center. aside from that, our universe is perfect, and circles are perfect, and ovals are not perfect. Do you believe that? So the other thing was, we all think, and sometimes we see these images of the shape of the orbits of the planets are circles. And that was hard to break from. And Kepler's first law says, nah, it's not a circle. It's actually a little bit elongated in what I would call an oval. A fancy name for an oval is an ellipse. Okay, so an ellipse. That was a big, hairy deal. If you go ahead and go from circle to ellipse, you can kind of account for the anticipating where the planets are going to be. Okay, so that was very important. All right, so his three laws are right here. I'm going to kind of take you through each one of them. His first law, Kepler's, who I'm talking about, said that, and all of Kepler's laws deal with planetary motion. His first law said that the shape of their orbits are not circles, they're ellipses. We'll talk more about what an ellipse is. His second law, summarized, says that, and I've already been kind of talking about this, that the planets move faster. No, I haven't been talking about this. This other one, when I talk about the orbits of the planets, we're going to see that the sun is offset from being center, which means that sometimes the planets are closer and sometimes the planets are farther away. And we're going to see, and I'm going to kind of use like a racing car going, like to speed up, okay. So they speed up when they're closest and they slow down when they're farthest away. This other one says that, now this is kind of what we talked about, that literally Mars moves more slowly in its orbit around the sun than the Earth does. The Earth moves faster, Venus moves even faster, and Mercury moves the fastest. And sometimes I'll have students, it seems like just the other day I was talking about this with a group of students, are like, well, is that a gravity thing? Yes, that's a gravity thing. Okay, the farther they are from the influence of the mass of our sun, the more slowly they move in their orbits. So that kind of summarizes the three of them. So let's talk about his first one. So you see this oval right here, this ellipse. It's one of possible conic sections you can get by taking a cone, blah, blah, blah. But it looks like an oval, doesn't it? The biggest thing I want you to know right here is that this is the shape of the orbit of the planets. So you can kind of see the ellipse here, and I mentioned the off-centeredness of the sun. So this blue could be the path of the Earth, it could be the path of Mars, it could be the path of any planet, and the sun is offset. Specifically, though, if you talk about, use the fancy word ellipse, ellipses are awesome. I'm going to show you an image here in a minute. They have two belly buttons. Okay, they're called foci. Foci. They're like sweet points in an ellipse. And so the sun is located at one foci. If you're like me, I'm like, well, what's at the other foci? Well, actually, so 6 months later, we can know what that is. So it's nothing. But I think we should make a science fiction movie. There's something at that other foci. Anyway, so you can kind of, what's that?
Directed by
Yes, directed by Professor Snipes. There's two important terms here that I want you to get a handle on. Peri means close, and helion means sun. So close to the sun is right here. Okay? Well, I shouldn't make that a star because that's the Earth. This is the Earth. Far from the sun is aphelion. It's over here. Now you might think, so when in the northern hemisphere, when is the coldest time of the year? What do you think? What month is it in?
Say again.
The coldest month of the year. Coldest month. January, February. I agree. Yeah, coldest month. I agree. So actually, perihelion occurs at January 1st. So the reason we're so dang cold, sometimes you guys want to use a stronger word than that, is because of the tilted Earth tilted axis of rotation. So we actually are closest here. This is perihelion, and this is aphelion. Then sometimes students will say, well, oh my gosh, what about southern hemisphere? So they're tilted. Okay, so they're having summer, and they're closest. So do they get a double whammy? And I think the answer to that is not necessarily. because the distance, I know I'm kind of exaggerating it, but the distance here is not enough to make a big difference. The thing that the southern hemisphere has going for it, it's 5 minutes, he's counting. The thing that the southern hemisphere has going for it is the difference between, actually if you look at the globe, we have a lot more land and they have less land and more water. So that's the biggest thing. That's Kepler's first law. So, and this is an ellipse. You can kind of see these two belly buttons. Okay, so this is a foci and a foci, and they're important if you kind of do like a little, this used to be a spirograph for you if you kind of make these little things. Okay, so if you take a piece of string and it's always the same length and you draw the shape around like that, you get it. One of the things we're going to refer to in Kepler's last law is this distance right here. Okay, this actually is called, make sure I got this right. This is called the semi-major axis. Semi meaning half, and it's the major axis because it goes along with the biggest chord of the ellipse. So this is showing you his second law. This is a meow. So what I meant to do or say is basically it goes real fast here, and slows down, and it goes the slowest here. Oh, darn it. I'm going the wrong way. Am I going clockwise? Darn it. Okay. Slow here, faster, 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 faster. Okay.
Too much fun.
I know, right? So what his law says is if you go ahead and make this time the same as this time, so I don't know if you kind of see how those could be time segments, the length of time it takes to travel from this distance to this distance, it's going slower out here, so it travels less of a, okay. And you go ahead and go back to the sun, these areas, these two areas that kind of look like triangles are the same. They sweep out equal areas. His last law, remember I showed you what A is? It's the semi-major axis of the ellipse. The ellipse is down, okay. So in science, we do this a lot. We look for what's called correlations, and sometimes we cube things, sometimes we square things like we've done here, sometimes we take the square root of, sometimes we take the natural log of. But honestly, if you take the P, which is how long it takes to orbit the planet, squared, it's approximately equal to the semi-major axis of the oval of that planet raised to the third power. Like, really? This is my least favorite one. But its consequences means that the farther out the planet is, the greater the A, the greater the P. The greater period means how long it takes to complete one orbit. So I'm good with that. So after Kepler, now we have Galileo. And there's some overlap. I have to look back at the days when they were born and died and all that. Galileo, very smart guy. So Galileo came after the whole Copernicus revolution from Ptolemy's idea, the heliocentric model of our universe at the time. So Galileo saw these three things were obstacles to really believing that the Earth orbits the sun. The first one is if the Earth did orbit the sun, then everything on the Earth as it moved would fly off. Okay? Because, like, for instance, if I had, you know, this is the Earth, and this is, like, stuff on the Earth, as I move, it's going to fly off, right? So he had to kind of say why that's not the case. Anybody got their slides printed out? Up there, 1, 2, 3. I'm going to get you next homework. Correct. I'm going to go ahead and wrap it up today. And so there's no homework due over the weekend? I know, but you still have enough knowledge. You actually can, if you want to work ahead, work on those problems. Okay? This is so cool. We'll pick up with Galileo on Monday.